Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, FDM wireless communication systems. Now, in the last module, we have seen a metric to characterize the delay spread of a wireless communication system, that is the maximum delay spread. Now, let us look at another metric. Now, the maximum delay spread might not be a very appropriate metric to characterize the delay spread of a wireless communication system for the following reason. For instance, if you look at the wireless power profile, there are some dominant paths with a large amount of power, but as you go towards the end, there might be a large number of small paths, rather spurious paths with a small amount of power. So, there might be in your power profile, if this is my power profile or my multipath power profile, there are a large number of paths or spurious components with negligible power. There can be a large number of paths with negligible power, and these are also known as spurious components. Which might not really be signal components, because sometimes these small power paths might in fact be below the noise threshold. For instance, let us say I have a noise threshold. So, this is let us say my noise floor. These multipath components lie below the noise floor. So, therefore, it is very difficult to distinguish these multipath components, these signal components from the noise. So, these can be spurious components, these might not be signal components at all, right. And therefore, the RMS, the maximum delay spread, which looks at the maximum difference between the first and the last arriving components, might not be a metric, reasonable metric, because it is affected by these spurious components which are arriving towards the end. Right, because the maximum delay spread does not consider weighing by the appropriate gain of each path. So, therefore, the maximum delay spread in such scenarios with spurious components, maximum delay spread might not be an appropriate metric. So, we have to consider something more appropriate, and that is the RMS or the root mean square delay spread. So, the metric that we would like to consider is known as the RMS delay spread. This also stands for the root, short for the root mean square, that is the RMS. So, in this scenario, we would like to consider the RMS or the root mean square delay spread, and this is calculated as follows. For instance, let us go back to our multipath power profile with L components. For instance, component G0 corresponds, gain 0 corresponds to delay tau 0, gain G1 corresponds to delay tau 1, gain GL minus 1 corresponds to delay tau L minus 1. That is, GI is the, I hope everyone remembers the notation, GI equals gain of ith path and tau I equals delay tau I equals the delay of the ith path, and I have L multipath components. I have L multipath components where G naught is the gain of the 0th path and tau naught is the corresponding delay. G1 is the gain of the first path, tau 1 is the corresponding delay, so on and so forth. GL minus 1 is the gain of the L minus 1th path and tau L minus 1 is the corresponding delay. Now what we want to do is, first we want to compute the average delay. So we want to compute the average delay which I am going to denote by tau bar, and this is given as follows. Let us say the fraction of power in the ith path I denote by Bi, the fraction of power in the ith path, that is Gi divided by summation I equal to 0 to L minus 1 or summation j equal to 0 to L minus 1 Gj. What is Bi? Bi is the fraction of power in the ith path. So the fraction of the power Bi in the ith path is Gi, the gain of the ith path, divided by summation of Gj, j equal to 0 to L minus 1, which is basically the total power. So this is basically what I am doing is basically the fraction in the ith path is power of ith path divided by the total power. This is the fraction of the power in the ith path, that is Bi equals Gi divided by summation j equal to 0 to L minus 1 Gj. And now we can compute the average delay by weighing by the fraction of the power, by weighing each delay by the tau I by the fraction of the power Bi in the ith path. So the average delay tau bar, so this is my average delay this is equal to B naught T naught plus B1 tau 1 so on up to BL minus 1 tau L minus 1. This is what am I doing? I am basically weighing each delay tau I by fraction of power beta I. I am weighing each delay tau I by the fraction of power Bi in the ith path. So that is B naught tau naught plus B1 tau 1 plus so on up to BL minus 1 tau L minus 1, which can be written as basically, which is equal to summation I equal to 0 to L minus 1 Bi tau I. Now Bi remember is Gi divided by summation Gj. So I can in turn write this as summation I equal to 0 to L minus 1 Gi tau I divided by summation j equal to 0 to L minus 1 Gj. Now I can finally simplify tau bar as summation I equal to 0 to L minus 1 Gi tau I divided by summation I equal to 0 to L minus 1 Gi. So this is my expression for the average delay. This is my expression for the, let me remind you, this is the expression for the average delay tau bar, which is summation I equal to 0 to L minus 1 Gi tau I divided by summation I equal to 0 to L minus 1 Gi. This is the average delay of the multipath power profile. Now what we want to do, we would like to characterize, we would like to compute the RMS delay spread, and the RMS delay spread is given by the deviation of this multipath power profile about the average delay. So how do I calculate the deviation? The deviation, so the deviation sigma tau square, the square of the deviation is basically, from statistics you know, B naught tau naught divided minus tau bar square plus B1 tau 1 minus tau bar square plus so on plus BL minus 1 tau L minus 1 minus tau bar square. So this is the square of the, so sigma tau square is basically the square of the deviation. That is, what am I doing? I am taking each fraction of power Bi multiplying by the square of the deviation, that is tau I minus tau bar square, that is square of the deviation about the average delay. So this gives me the squared deviation, and when you take the square root of this, I get the root mean squared deviation or the RMS delay spread, and therefore sigma tau is equal to basically the square root, or sigma tau is equal to well, I can write this simply as summation I equal to 0 to L minus 1 Bi tau I minus tau bar square raised to the power of, whole raised to the power of half. And now I can substitute the values of Gi here, and therefore if I substitute the values of Gi, I get sigma tau equals summation I equal to 0 to L minus 1 Gi tau I minus tau bar whole square divided by summation I equal to 0 to L minus 1 Gi whole raised to the power of half, or basically the square root of this quantity, that is the standard. That is, now we have this sigma tau, which I can call the RMS delay spread, which is equal to the square root of summation of I equal to 0 to L minus 1 Gi tau I minus tau bar square divided by summation I equal to 0 to L minus 1 Gi, the square root of this entire quantity, that is the root mean squared delay spread, which is basically the deviation of the power, deviation of the, or the spread of the power, the square root of the spread of the power about the average delay, that is tau bar. This is the RMS delay spread. Okay. And I can also now substitute for Gi, instead of Gi I can also substitute magnitude Ai square, and this is how you will find it written conventionally. Remember, our Gi equals magnitude Ai square, where Ai is the amplitude of the ith path. So I have sigma tau is equal to square root of summation I equal to 0 to L minus 1 magnitude Ai square tau I minus tau bar whole square divided by summation I equal to 0 to L minus 1 magnitude Ai square whole raised to the power of half, that is square root of this quantity which is given, which is the basically the RMS delay spread. Let me write this clearly. This is the RMS delay spread of the multipath power profile. This is the expression for the root mean square delay spread or the RMS delay spread of the multipath power profile. Let us now do a simple example to understand this better. So let us do a simple example. For instance, let us consider again a scenario with L equal to 4 multipath components. let us consider a scenario with L equal to 4 multipath components, and this scenario is as follows. Let us say the delays are given as follows: tau naught is equal to 0 microseconds, tau 1 is equal to 1 microsecond, tau 2 is equal to 3 microsecond, and tau 4 is equal, and tau 3 tau 3 is equal to 5 microseconds. These are the various delays: tau 0, tau 1, tau 2, tau 3 of this 4 component multipath power profile. And now let us look at the various gains. I have G naught equals 0.01 equals minus 20 dB, because 10 log to the base 10 of 0.01 is minus 20. G1 equals 0.1, which is equal to minus 10 dB. G2 equals 1, which is equal to 0 dB, and G3 equals 0.1, which is equal to minus 10 dB. And now what we would like to do is, let me first draw a picture to sort of illustrate what is going on in this channel. I have a multipath power delay profile with 4 components. So I have a 4 component multipath power delay profile, and basically the first component, so I have different levels. Let me draw different levels here: minus 20 dB, minus 10 dB, and 0 dB. So let us call this as minus 20 dB, minus 10 dB, and 0 dB. And let us have 0 microseconds, that is intervals of 1 microsecond. I have 2 microsecond, 3 microsecond, 4 microsecond, and 5 microsecond. At tau equal to 0, and this is my tau scale, at tau equal to 0 microsecond, I have a path which is of gain G naught equals minus 20 dB. At tau equal to 1 microsecond, I have a gain G1 at which is equal to minus 10 dB. At tau equal to tau 2 equals 3 microseconds, I have G2 which is 1, which is basically 0 dB. This is my G2. And at tau is equal to 5, tau 3 is equal to 5 microseconds, I have G3 equals 0.1, which is basically equal to minus 10 dB. So this is my multipath power profile drawn on the dB scale. So this is basically my multipath this is basically the multipath power profile I have, which is drawn on the dB scale. Let me also write it in a tabular form. So I am going to write it also in a tabular form, so that it's clear what are the gains and the delays, the various gains and the delays that we are dealing with. Let me make a couple of columns here, that is the delay tau, then I have the dB gain, then I have the actual gain G, and then let me also write A, which is the amplitude, which is the square root of square root of G. At tau is equal to 0 microsecond, I have the dB gain minus 20 dB, which means my G equals 0.01, and the amplitude A, which is square root of G, equals 0.1. At tau is equal to 1 microsecond, I have my dB gain, which is minus 10 dB, I have, which means G equals 0.1, and A, which is square root of G, is 0.3162. At 3 microsecond, I have my dB gain, which is 0 dB, and G equals 1, which is 0 dB. At 5 microsecond, I have my dB gain, which is minus 10 dB, which means the gain is 0.1 and the amplitude is 0.3162, and this is square root of 1, which is 1. So, basically I have, this is the tabular form of, so this is a tabular representation So, this is a table representation of the various multipath components, the gains in dB, the gains in normal, and the amplitude, which is the square root of the power gain, and also the corresponding delay. So, this is a very convenient table that gives us a snapshot of the multipath power profile. And now what we want to do is we want to compute the RMS delay spread, and therefore we will start by first computing the average delay. And the average delay, as you know, is given as tau bar. So, we want to compute the average delay tau bar, which is equal to summation I equal to 0 to L minus 1 gi tau I divided by summation I equal to 0 to L minus 1 gi, and this is equal to, basically let me write this down explicitly over here, this is equal to the various gains multiplied by the corresponding delay. So, this is equal to 0.01 times 0 plus 0.1 times 1 plus 1 times 3 microsecond plus 0.1 times 5 microsecond divided by the sum of the gains 0.01 plus 0.1 plus 1 plus 0.1, and this is equal to 2.9752 microseconds. So, the average delay tau bar, this is the average delay So, the average delay tau bar is equal to 2.9752 microseconds. So, this is the average delay of this multipath, of the given multipath power profile under consideration. So, we have calculated this quantity tau bar, which is the average delay. And now, using this tau bar, we want to compute the RMS delay spread, and remember the RMS delay spread, that is sigma tau is equal to, basically in the numerator I have summation I equal to 0 to L minus 1 gi tau I minus tau I minus tau bar square divided by summation I equal to 0 to L minus 1 gi whole thing square root of the whole thing. Therefore, I can write my sigma tau as, and now I am going to write the entire expression, that is 0.01 g0 into tau 0, which is 0 minus tau bar 2.9752 whole square plus 0.1, that is g1 times 1 minus tau 1 minus 2.9752 whole square plus tau g2, that is 1 times 3, that is tau 3 minus 2.9752 whole square plus 0.1 times, that is g3 into tau 3 5 minus 2.9752 whole square divided by 0.1 plus 0.01 plus 0.1 plus 1 plus 0.1, and of course, for the whole thing I have to take the square root, and therefore, this is given as sigma tau is equal to 0.8573 microseconds, and this is given as the maximum, this is given as the RMS delay spread. Remember this is the RMS. So, the RMS delay spread sigma tau for this channel under consideration is 0.8573 0.8573 microsecond. Now, if you go back and look at the maximum delay spread, the maximum delay spread is simply tau 3 minus tau 0, that is the delay between the first and the last arriving components. Therefore, the maximum delay spread on the other hand, that is sigma tau max equals tau 3 minus tau 1 is equal to 5 microsecond. And therefore, what you can see is that the RMS delay spread is much smaller than the maximum delay spread. Is much smaller than the maximum delay spread. The RMS delay spread is much smaller than the maximum. RMS delay spread is 0.8573 microseconds, maximum delay spread is 5 microseconds, and this is arising because the RMS delay spread is actually weighing the delay of each component by the corresponding fraction. So, it is a weighted delay spread rather than looking at the maximum delay spread, which is simply the delay between the first and the last arriving components, which might not be an appropriate matrix. Therefore, the RMS delay spread, which weighs the delay by the corresponding power, is a much more appropriate metric, and we have seen in this example how to compute it. This is given as 0.8573 microseconds. So, we will conclude this module here, and we will explore other topics in subsequent modules. Thank you very much.